Today's lesson is more of a hodgepodge of everything to do with what we've learned in calculus so far. We're gonna look at a little bit of inverse trig functions. We're gonna look at the idea of some of the domain and range restrictions when we're talking about trig functions. And then we're gonna be doing some practice with inverse functions as a whole. And then I'm actually gonna give you some free response questions that were given years ago on the AP exam, and we'll go over them because this is the first time we have an opportunity to see a little bit more depth and breadth to the content of calculus to help us get the practice that we need to prepare for the AP exam. So with that said, let's go ahead and get started. Domain of inverse trig functions and their derivatives. Well, before we do that, let's just go back and get another practice problem with the idea of inverse trig functions. So here we have x of t is equal to arc cotangent of t, which can be you can just write that as cotangent -1 of t, right? Cotangent, arc cotangent. And that represents the motion of a particle along the x-axis when is the particle moving in the positive direction. So before we even go to answer this question, let's go ahead and interpret what the question is actually saying. We are looking for when the particle is moving in the positive direction. That would imply, let me write this down, moving in the positive direction implies that our velocity, that v of t, is positive. Okay? So that's our justification. That's telling us what we need to do. And remember, when we're talking about anything analytical, we need to approach it through understanding the signs of a function, right? We don't know direction of a function analytically. We know signs of a function analytically. So we want to break it down to when velocity is positive. So we need to take the derivative of this. We need to find the velocity. Well, to do that, because this is an inverse function, let's get rid of the inverse. I don't like doing inverses. So I'm going to go ahead and take the inverse of both sides. So I'll take cotangent of both sides in order to get rid of that. So we're left with cotangent of x of t. I'll just say cotangent of x equals t. Keeping in mind that t is our variable and x is the function. X is a function of time. So that when we go to take this derivative of cotangent of x, we're treating it as a function, which means we have to use implicit differentiation and therefore use the chain rule. So what's the derivative of cotangent? Well, derivative of cotangent is negative cosecant squared of x and then times x prime, because again, x is a function, equal to the derivative of t is just 1 because t is our variable. So we have negative cosecant squared of x times x prime, and then we can isolate x prime by just dividing. So we end up with -1 over cosecant squared of x. Now we can flip that up and say that that is the reciprocal of sine, so we could say negative sine squared. But remember, we want to get this in respect to time. So the next step is to get rid of this expression down here that's in respect to x. And the way we do that is we deal with our right triangle. Okay, so where does our information from our right triangle come from? It comes from our trig equation right here. Cotangent of x implies that x is my angle, x degrees or x radians, I should say. And then cotangent, remember, is adjacent over opposite, right? It's the reciprocal of tangent. And since tangent is opposite over adjacent, cotangent will be adjacent over opposite. So that implies that the t is adjacent and the opposite is 1. And then from there, we can do the Pythagorean theorem. So we would actually end up with the square root of 1 squared plus t squared, or just 1 plus t squared. Then we can answer, what is cosecant? What's cosecant? Well, cosecant is the reciprocal of sine, so it's going to be hypotenuse over opposite. So it'll be this over this, or just this, because that's just 1, and then square it. because we're squaring here. So then we're going to get 1 plus t squared. So x prime, and I'll put this down, x prime of t is equal to negative 1 over 1 plus t squared, and x prime is the velocity. So we've got what we need. Now we need to figure out when the particle or the object is moving in the positive direction. So we are looking for when velocity is positive here. So we would normally go through this big long process, setting the derivative equal to 0 and checking signs. I guess we could do that, but you're going to find that this particular problem can be thought through just mentally. When does the derivative equal 0? Well, it will never equal 0 because the numerator is not 0. Okay, so we don't have to worry about that. Well, when is it positive and when is it negative? The denominator is always going to be positive because the t squared is positive here. Since t squared is positive, this denominator will always be a positive value. And if that's the case, then we have a negative divided by a positive, which implies that x prime of t is always less than 0, right? Because we have a negative over a positive. Well, if that's the case, then the object is always moving in the negative direction. It's never moving in the positive direction. So we would say, therefore, never. And then if you want to add a little bit more, since v of t is never positive. All right, so that is our answer for that problem. That's a good example of just an oddball type of result that you can get from these types of functions. But we did get a good example of dealing with the derivative of inverse trig functions and application to particle motion. Let's go ahead and take a look at how I did it. I think I approached it a little bit differently in the lesson. Again, I set y equal to arc cotangent of x instead of saying x of t. So instead of saying t is the variable and x is the function, I said x is the variable and y is the function, just because that's, that way we're kind of used to it. But we don't want to necessarily express that like on the AP exam unless we're clear, because that can cause confusion. The x here does not represent the x in the description here. But anyways, take the cotangent of both sides, take the derivative of that, and notice I actually went back to the definition of cotangent being cosine over sine, because maybe I don't remember the derivative of cotangent directly. Maybe I don't remember it's negative cosecant squared. So we're going to have to apply the quotient rule here. So the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. This method is actually giving us a lot of good practice with the idea of implicit differentiation. So I would highly advise making sure you understand the process that's on the lesson as well as what's on the board here. Okay, and then again, the derivative of the right-hand side is 1. This all simplifies. Well, in this case, I just factored out a y prime from the top two expressions, and then I multiplied by sine squared y, and oh, this is interesting. This is very interesting here. Didn't see this coming here. I actually factored out a negative y prime, and the reason I did that is because they both have a negative. And notice what I have. I have sine squared of y plus cosine squared of y. Well, sine squared plus cosine squared is 1. That's the trig identity. So since that's 1, I really just have y prime over sine squared y equals 1. And then isolating y prime, I would just multiply both sides by sine squared and divide by 1. So I'm left with y prime equals negative sine squared of y. And that's exactly what this is. It's negative sine squared of y because it's the reciprocal. Now, with that said, I didn't even go into the triangle because I recognize that any number squared cannot be a negative number. Sine squared has to be 0 or it has to be positive, essentially. And when I multiply that by a negative number, that means the result has to be 0 or negative. Now, we know it can't be 0, but the answer still remains the same. We cannot get a positive result out of this, and therefore the particle is never moving in the positive direction. So I guess I did do the triangle here, and same setup as I have here, and then we would say that we end up with negative 1 over 1 plus t squared, or 1 plus x squared, and since that is never a positive number, then we know that we are never moving in the positive direction. All right, that's a good practice problem right there. All right, just real fast, going to kind of go over this pretty quickly. You should be familiar with the idea of inverse functions. Remember that the domain of a function should be, in a sense, the same as the range of its inverse, right? Now, if those functions are not one-to-one, that we have to restrict the domain of the original function so that we actually get a function of the inverse, so that the inverse is actually a function, okay? But regardless, when we talk about inverses, the domain of the original equation is equal to the range of the inverse equation, all right? So here's an example of this, dealing with trig. Y equals sine of x. Well, the domain of sine of x is negative infinity to infinity, and the range is from -1 to 1. Well, if I want the inverse of that, now the inverse of that would just be the arc sine, right? The arc sine of x. The domain and the range switch. So we would say that the domain is from -1 to 1, and the range is from negative infinity to infinity. But we have a problem with that, because if I take the inverse, remember the inverse graphically is reflecting the trig function, or any function, along the line y equals x. And when I do that, I end up with this squiggly that's going up and down. Well, we can easily see that this is not a function because it fails the vertical line test. So what we need to do is we need to restrict our range so that it is a function. And what we do is we talk about basically the values that are right around the origin. And so we're going to erase, essentially, everything that is below a certain point and everything that's above a certain point, so that we get the entire domain from -1 to 1 still, but none of the range values repeat. Or sorry, none of the domain values repeat for the range. So that would imply that the lowest y value would be -π/2, and the highest y value would be π/2. Because same thing here, well, if I go back to -π/2 for this domain, I get -1, and when I go to the right π/2, I get +1, and so I don't get any repeating values. And so we would change the range so that this remains a function to be -π/2 to π/2. Just wanted to bring that up for various reasons. You'll see why in the future. But with that said, let's go ahead and take a look at another example of an inverse function. Now, this function that we're dealing with is not a trig relationship. It is just the idea that we have inverse functions. And it's really going to be beneficial for us to see this, because this always pops up on the AP exam in one form or another. So it says that f of x is 3x minus 2 squared. F of x is 3x minus 2 and then all squared. And then it tells us that g is the inverse of f. So I'm going to go and write that down. G of x is the inverse of f of x. And we're going to want to make sure that we have an equation that makes sense that we can work with. G is the inverse of f. And then we also know here that f of 2 is 16, and we are looking for g prime of 16. Interesting. Looking for g prime of 16, that's the question. So really what we need is we need to figure out the derivative of g. So if we look at this function, that doesn't really help us out too much because that's all about f. We need to be talking about g, and pay close attention to this because this idea is going to, again, repeat itself throughout the rest of calculus. Well, how can I take the derivative? Well, if I want the derivative of g, here I have a function g. G of x equals the inverse of f. So all I would have to do is take the derivative. So let's go ahead and do that. Let's take the derivative of this equation. Well, if I take the derivative of the left, I get g prime of x. I don't know how to take the derivative of an inverse function necessarily. So there's a way to do it, but again, I would rather understand the process of how it comes to be instead of just memorize the results. So I don't like inverse functions. I don't like them. How could I get rid of it? Let me go ahead and write this down. I'm going to just rewrite this down here so I have some room to work. I have G is the inverse of f. Well, how do I get rid of an inverse function? I take the f of both sides. If I take the f of this, those are going to cancel out, just like we talked about the other day. The f of the inverse of f just gives us x. But if I do it to that side, I have to do it to this side. And so, as a result, I end up with f of g of x equals x. Now, I could take the derivative of this. Because I don't have any inverses, this isn't disgusting, but what I want to remember is that I have to apply the chain rule. Because I have a composition of functions, we have an inside function here, we call it g, we have to apply the chain rule. So what's the derivative of f of something? Well, that would be f prime of something, and then times the derivative of that something. So it would be times the derivative of g, which is g prime of x. And then you could even argue, well, we have something inside of the g. It's x. So what is the derivative of the x? Well, times 1. Okay? And then that is equal to the derivative of x over here, which is 1. So now I have an equation that has g prime in it, right? And so let's go ahead and isolate g prime by dividing by f prime of g of x. So we end up with g prime of x is equal to 1 over f prime of g of x. And so we have this equation. Now, if I want g prime of 16, g prime of 16 means that I am plugging 16 into x. So I end up with 1 over f prime of g of 16. Okay? And now we just got to evaluate this. Well, this is going to take some of your basic understandings of inverse functions back from Math 3 or from Algebra 2. We have 1 over f prime of g of 16. Well, to evaluate this, we would need to know what g of 16 is. But I am not given anything about g over here to evaluate. But I do have this relationship that says g is equal to the inverse of f. Well, remember, what does that mean? If two functions are inverses of each other, that means their x and y's flip. In other words, if in one equation we have, or one function, we have this relationship, this coordinate of 2 comma 16, for f has the coordinate of 2 comma 16, that would imply that g, which is its inverse, has a coordinate of 16 comma 2. That's interesting, right? Now, another way to write that, I guess you could say, is since f of 2 is 16, that implies that the inverse of f of 16 is 2. And since g is equal to the inverse of f, we could say that g of 16 is 2. That's an important relationship that always pops up. Well, now I can use that idea to tell what g of 16 is. Well, g of 16 is 2. So we could say that g prime of 16 is 1 over f prime of 2. And so from here, we just need to figure out what f prime of 2 is. Well, now I can go to this function and figure out what f prime of 2 is. So taking the derivative of that, we would say f prime of x is equal to, well, I'm going to apply the chain rule. I could multiply this all out and do the power rule, but I'm going to apply the chain rule. The outside function is something squared, so the derivative of that would be 2 times something to the first power, and then times the derivative of the something, so the derivative of 3x minus 2 is 3. And then we can simplify that a little bit and say f prime of x is equal to, let's see, that's 6. That's going to be 18x minus 12. And because I wanted f prime of 2, I'm going to plug 2 in there. So I got f prime of 2 is 18 times 2 minus 12. So that's 36 minus 12, which is 24. And so we're left with f prime of 2 equals 24. And then I can take that and plug it in here. So we end up with g prime of 16 is equal to 1 over 24. Boy, that's a bit of a process. That's a long bit of work there to just deal with inverse functions. But that's kind of cool that how the inverse function is related and how we can take the derivative of an inverse function by doing some algebraic manipulation. So how do we do that? We got rid of the inverse function by taking the f of both sides. And so now I have a composition, which implies I have to use the chain rule. Okay? The other key to this is this idea that if these two are inverse functions, that means the xy of f need to flip to get to the xy of g. All right, so let's go ahead and double check to make sure I'm good here. Notice I actually approached this a completely different way on the lesson. What did I do? I noticed that g and f are inverse functions, so I took my f function, I said that that is y, and I found the relationship of g by isolating y at that point, just like I would in any inverse function. And then I can take the derivative of that by just using the power rule. So I'm left with 1/6x to the negative 1/2. And then if I want g prime of, and simplify that a little bit further, if I want g prime of 16, then I would plug 16 into x, and I would end up with 1 over 6 times rad 16, which is 1 over 24. Now, you're going, well, why in the world did you do all of this work when you could have just done it the way you did it in the lesson? And I would agree with you if that's possible. Most of the time, though, the way these questions are posed, it won't give you f of x directly, right? So you're not going to be able to go through the work of finding the inverse of that in order to figure out g. So instead, we deal with the function notation and work with the function notation. And this actually, I think, is more elegant in a sense, okay? All right, so the next thing I want to do is I want to go over a couple free response questions that were given quite a few years ago on the AP exam, and it will give us kind of an idea of what to expect when it comes to what we've been talking about the last few lessons, okay? I have two problems here, and I'm going to put them off to the side here so you can see them. And what I would like you to do is pause the video and do it yourself. Normally a free response question should take no more than 15 minutes. So go ahead and set a timer for 10 minutes and see how much you can get done in that 10 minutes, and then come back and compare your results to mine to see how you did, okay? So the first one we're going to do is actually from 2004. This was number 4 from 2004. So here we have an equation that says x squared plus 4y squared equals 7 plus 3xy. And in part A, it's asking us to show that dy dx is equal to 3y minus 2x all over 8y minus 3x. So it's telling us what the derivative is, and it's just asking us to show the work for why that's true. So we've got implicit differentiation here. We want to show this. Okay. So we're going to go ahead and take the derivative of this, keeping in mind that y is the function and x is the variable. So what's the derivative of x squared? Well, that would be 2x. The derivative of 4y squared, using the power rule, we get 8y. But then we have the chain rule here because that's a function, so times the derivative of the inside thing, so times y prime, equals the derivative of 7 is 0. Here we have a product rule, so I'm going to identify 3x as my first function and y as my second function. So the derivative of 3x is just 3, and then times the second thing is y, plus the derivative of the second thing, which is y prime, times the first thing, so times 3x. Now I want to isolate y prime here because the goal is to figure out what y prime is. So I'm going to move all of this over here, and then I'm going to move the 2x over there. So I end up with 8y times y prime minus y prime times 3x equals 3y minus 2x. And then you should be able to see now I can factor out a y prime. So we end up with y prime times 8y minus 3x equals 3y minus 2x. And then divide, so we end up with y prime equals 3y minus 2x over 8y minus 3x. And that's exactly what they told us to show. The only thing that you could say is, well, this is in Newton's form, that's in Leibniz form, so let's just go ahead and rewrite it in Leibniz form so that everybody is happy. Okay, so we have shown the derivative is that. Right. Okay, for part B, it says, show that there is a point with an x-coordinate of 3 at which the line tangent to the curve at P is horizontal. So since I want the tangent line to be horizontal tangent, that implies, so therefore that implies that dy dx has to equal 0, because if we have a horizontal tangent line, that means we have a slope of 0. Horizontal tangent means that the slope is 0. So all I have to do then is plug in 0 for my derivative, and so I'm left with 0 equals 3y minus 2x over 8y minus 3x. But then it also said show that we have a y value when x equals 3. When x equals 3. So we're going to go ahead and plug in 3 here. So we end up with 3y minus 2 times 3 all over 8y minus 3 times 3. And obviously the denominator doesn't mean anything. It's just the numerator, because when I go to multiply all this, or cross multiply, however you solve it, you're going to get 0. So you end up with 0 equals 3y minus 6. And then solving there, we get 6 equals 3y, so y equals 2. So what we did is we actually found the y value first. We did the second part of this because it says find the y coordinate of p. But what we need to do, what we need to make sure, is that we double check to make sure that this point, this coordinate of 3, 2, actually lies on the original curve. And so what we'll do is we'll plug in the x and the y values to make sure that makes sense. So we would end up with 3 squared plus 4 times 2 squared, and we're checking to see if that's equal to 7 plus 3 times 3 times 2. And so we end up with 9 plus 16 equals 7 plus 18, and in fact 25 does equal 25, and therefore we know that the coordinate 3, 2 is on that curve, and when x equals 3 and y equals 2, we have a horizontal tangent line, a slope of 0. So that's part B. Part C, it's saying find the second derivative at the point found in part B. So I'm going to go ahead and write this down. I'm going to say for part B, because I got to erase some of this stuff, I'm running out of room. The point that we got for part B was 3, 2. So we know that P is 3, 2. Okay? And we are looking for the second derivative at that point. So here is the first derivative, and we need to find the second derivative. So that should be pretty straightforward. To find the second derivative here, we're going to say d2y over dx squared equals, and we're going to have to apply the quotient rule. So the derivative of the top is going to be 3y prime minus 2, and then all times 8y minus 3x, minus the derivative of the bottom, which would be 8y prime minus 3, times the top, which is 3y minus 2x, all over the bottom squared, which is 8y minus 3x squared. Now, we don't have to. Normally, I would say, since I want the second derivative, in, hold on a second here. So we don't have to figure out what the second derivative is in respect to x. We're not looking for the function, the second derivative function necessarily. We're just looking for the second derivative at that point. Normally, though, we would have to replace y prime with all of that to say the second derivative is this. Normally, they don't ask us to do that, but sometimes they do, and that would require a lot more work. But since I only want the second derivative at this point, I'm just going to plug 3 and 2 into my x and y values. And so d2y over dx squared evaluated at 3, 2 is going to be equal to 3y prime minus 2 times 8y, which is 2, minus 3 times 3 for x, minus 8y prime, minus 3, times 3y, so 3 times 3, minus 2 times, 3 times 2 minus 2 times 3. Did I do that right over here? 8 times, yeah. Over 8y, so 8 times 2 minus 3 times 3, all squared. Now notice we can't actually solve this because I don't know what y prime is at this point. So I'm going to go back to my y prime function and also plug in x and y there to figure out those values. So we would say dy dx evaluated at 3, 2 is going to be 3 times 2 minus 2 times 3 all over 8 times 2 minus 3 times 3. And that's going to be 3 times 2 is 6. That's going to be 0 over, it doesn't really matter what that is, it's just going to be 0. And so we know that the first derivative is 0, and we knew that anyways because we knew that it had a horizontal tangent at that point from part B, so I didn't even have to do that. We know that y prime is 0 on this coordinate, so we can replace the y primes here, and then we can simplify it from there. So we end up with negative 2 times, let's see, that's 16 minus 9, 16 minus 9 is 7, and then minus negative 3, and then that's going to be 6 minus 6, which is 0, all over. 16 minus 9 again is 7, all squared. Simplifying that further, we end up with negative 14 on top, 49 on the bottom, and that can simplify to negative 2 over 7. And so we end up with the second derivative at that point being negative 2 over 7. All right, so that is one FRQ that I wanted to go over. And let's go ahead and take a look at one more FRQ. Check my time here, we're okay. This is from 2002, which is even further back. Boy, oh boy, this is older than some of you guys. All right, it says an object moves along the x-axis with an initial position of x of 0 equals 2. We're not going to actually need that concept or that idea in this problem. That was, I actually took only a piece of the free response question out because we can't answer the other part yet. But we know that the velocity is given by sine of pi over 3t. And we are looking for, in the first one, what is the acceleration of the object when t equals 4? So really, part A is asking us for a of 4. That's what it's saying, okay? Now, this is going to be a calculator-based problem, so it shouldn't be too bad, honestly. But just for good measure, to find acceleration, remember, that's taking the derivative of velocity. And we can actually do this without a calculator because we actually know the derivative of a trig function. We can use the chain rule. So the derivative of sine is cosine of pi over 3t, and then times the derivative inside, which would be times pi over 3. So a of 4 is going to be pi over 3, just moving that out front, times cosine of pi over 3 times 4, which is, let's see here, cosine of 4 pi over 3. Now I'm going to have to think. Cosine of 4 pi over 3, well, that's going to be 4 pi over 3. Let's see, that's 1 pi, 2 pi, 3 pi, 4 pi. So cosine is going to be negative 1/2 there. So pi over 3 times negative 1/2, which would end up being negative pi over 6. So that's a of 4. Okay. Now, with that said, again, this was a calculator-based problem, so we didn't really need to do all that, and I would argue that you shouldn't be doing all of that if this is a calculator-based problem. Really, all you need to do for this work is to say that I want the acceleration at t equals 4, so that is equal to the derivative of the velocity when t equals 4. You want to express that because that tells the AP reader that you know what to do, that you know that relationship between acceleration and velocity. And then from there, we'll go ahead and type that into our calculator, take the derivative of the sine of pi over 3x, comma x, close parentheses, evaluate it when x equals 4. And so we end up with negative 0.524. So a of 4 is negative 0.524. And if I check my work here, negative pi divided by 6 is in fact negative 0.524. Either one will work, but you're spending a lot more time doing it this way if it's a calculator-based problem. So that's part A. All right, for part B is asking which of the two statements are true. And in statement 1, it says the velocity of the object is decreasing over that interval. So we have to go through the work to develop the idea of where velocity is decreasing. Remember, velocity is decreasing when acceleration is negative, right? Thinking of the chart, so important to understand this, right? Velocity is decreasing when its derivative is negative. So we're going to actually have to take the derivative now in this case. So a of t is equal to, we're going to apply the chain rule here. So thinking that pi over 3t is the inside function, so the derivative of the outer thing would be cosine of pi over 3t, and then times the derivative of the inner thing, which is just pi over 3. Okay, I'll just rewrite that real fast to be pi over 3 times cosine of pi over 3t. So we are looking for when the acceleration function is negative, and so the first thing we have to do is figure out when acceleration is 0. Okay, so we're going to use our calculator to determine this now. So in your TI-89 or some equivalent, you'll store this into your y-list, and then you'll go ahead and graph, looking at the interval specifically from 3 to 4.5. We have a 0. We have a couple zeros, actually. We have a 0 at upper bound, lower bound, all this stuff. The first 0 occurs at 1.5. The second 0, and I guess you could do this analytically. It's possible. But boy, a lot of work. Okay. The next one is 4.5. So these are the zeros of acceleration. And we know that we're looking at, time is greater than or equal to 0. But we also know that we don't want to go past 4.5 really, because we're only looking at that interval on that statement. So we have zeros of 1.5 and 4.5. And that's also an endpoint here as far as we're concerned. But if you look at the graph that's given, we can determine the acceleration, the sign of acceleration. We could plug in values in between and figure it out, but we could just look at the graph. The graph looks something like this. It starts high, and then it goes low, and then it goes high. So this is 4.5 right here, and this is 1.5. So we can see that our acceleration is positive because it's above the graph here. This is our acceleration graph. And then it goes negative, and then after 4.5 it goes positive. But that's not such a big deal there. What do we see? We see over the interval 3 to 4.5, we see that the acceleration is negative. And so we can see that the velocity is decreasing. So we can say statement 1 is true. So statement 1 is true since a of t is negative over, what was the interval? Over 3 to 4.5. Okay, so statement 1 is true since acceleration is negative over that interval. All right, the second statement then says the object's speed is increasing. Well, let's justify that. How do I know when speed is increasing? Speed increases when v of t and a of t have the same signs. Well, over the interval of 3 to 4.5, we already know that the acceleration is negative. So now we've got to figure out where the velocity is negative, or if the velocity is negative there. So we'll go ahead and take our velocity function, and we'll find out where that is positive and negative. All right, so set that equal to 0. And have that stored in your calculator. Put that in your y-list, find the zeros. The 0 of that guy is going to be, let's see here. It looks like t equals 3 is my 0. I'm going to do that one more time just to make sure I am correct. Bound. Okay, come on now. Lower bound. Upper bound. Okay, so we have t equals 3, and it looks like we might have a 0 at the endpoints and whatnot. But this graph starting at 0 and going to 4.5, we know that the velocity is 0 at t equals 3. This is my velocity, and this is my acceleration, just to be clear. We can see that the graph does something like this. It starts at 0, and then it goes up, and then it goes down like that. So we can see that velocity is positive and then negative. Okay? So as a result, we can see that over the interval 3 to 4.5, from 3 to 4.5, our acceleration is negative, and our velocity is negative. Therefore, statement 1 is true, or sorry, statement 2 is true as well. And again, the justification is true since v of t and a of t have the same signs over 3 less than t less than 4.5. All right, so that wraps up part B, and that's as far as we can go with that particular free response question. Hopefully you have a good feel for how maybe some FRQs are going to look in the future, because we're going to start diving in deeper and deeper into that FRQ process. And especially when we get really close to the AP exam, we're going to be doing tons of free response questions to help prepare you for that. But hopefully you have a good idea of a little bit more of particle motion, a little bit more of inverse functions, their domains, range, things like that. How to take the derivative of an inverse function is so important as we move forward. If you have any questions, please comment below. Don't forget to like and subscribe, and I'll talk to you later.